Hey everyone, physics adventurers! Welcome! Our Spacetime Hack Relativity series is finally reaching its grand finale today. Wow! In our last training, we used that incredible map called the Spacetime Diagram to visually decode the mysterious physics engine of our universe. Things like time dilation, length contraction, and the relativity of simultaneity. By now, I bet you've built a pretty solid intuition for how spacetime warps, right? But intuition isn't enough. We need the weapon of pinpoint calculation. Today's quest is all about placing that final puzzle piece. Are you ready, team? Let's jump into this open-world journey to unlock the laws of physics together. All right, look right here on our screen. Here are the 3 treasures you're going to unlock in today's quest. Treasure number 1. Precise diagram construction. Until now, you were just looking at ready-made graphs, but today, you'll set your own skewed axes using the relative velocity ratio v/c. Once you can draw your own map, 80% of the problem is as good as 1. Treasure number 2. Total calculation hack for spacetime phenomena using Lorentz transformations. In our last video, we grabbed a visual intuition for time dilation and length contraction using graphs, right? Now I'm going to teach you the technique to plug those into the Lorentz transformation equations and calculate precise values for any given condition. And treasure number 3, relativistic velocity addition. Let's dive straight in and hack our first treasure. All right, companions, now we're jumping straight into treasure number 1, training to draw a spacetime diagram completely from scratch. Look at the slide. Here is our key strategy. Depending on the rocket's velocity v, both the slant of the axes and the scale of the grid will shift completely. First, calculate our most critical parameter, gamma, the Lorentz factor. Look at the equation on screen here. For example, as shown on the slide, if the rocket speed is 0.6 c, then v/c equals 0.6. Plugging that in gives gamma equals 1 over the square root of 1 minus 0.6 squared, giving us exactly 1.25. Once velocity v is decided, gamma is fixed. Next, let's draw the CT prime axis. The true identity of this axis is simply the world line of the rocket itself. How do we determine the slant? The slope is always c over v. If v equals 0.6 c, our slope is 1 over 0.6. As you can see on our diagram, the CT prime axis passes right through coordinates like 0.6, 1, and 1.2, 2. Once our time axis is set, next comes our space axis, x prime. In special relativity, you fold the x prime axis upwards symmetrically with the CT prime axis around the 45-degree world line of light. Think of it like closing a pair of scissors symmetrically from both sides. Now, how do we set the scale ticks? On the CT prime axis, the height where CT equals 1 for stationary frame S corresponds to CT prime equals gamma. For our example, where v equals 0.6 c and gamma is 1.25, a height of CT equals 4 gives CT prime equals 5. We will see this tip later. And the position x equals 1 corresponds to x prime equals gamma. And just like that, our x prime axis is complete. And here's something really important to notice. Look at the point where x prime equals 2 and CT prime equals 2. This point lies on the 45-degree world line of light. This is the beautiful part. Even though the x prime axis and CT prime axis themselves tilt depending on the rocket's velocity, the world line of light never changes from 45 degrees, no matter the speed. Einstein's ultimate foundational rule, the constancy of the speed of light, is perfectly preserved. Now, our setup for drawing maps is 100% complete. Now, we're going to use the exact Lorentz transformation equations to convert coordinates between reference frames. Lorentz transformation might sound like an intimidating boss name, but look at the slide summary. Switching your perspective to a whole different set of axes is the Lorentz transformation. Whether you read the scale visually off our map or calculate it with equations, the result is 100% identical. Let's look at the top box on screen for transforming from Earth frame S to moving rocket frame S prime. Ct prime equals gamma times Ct minus V over C times X, and X prime equals gamma times X minus V times T. Maybe the version in your formula booklet has both sides divided by C like this, but I recommend converting it to the form shown here and using this version instead. It's much more convenient to work with. Now, let's test this weapon with a concrete example. Look at point S on the graph with coordinates x equals 2 and ct equals 6. If the rocket speed v is 0.6 c, we already know gamma is 1.25. Plug them into the formula. Ct prime equals 1.25 times 6 minus 0.6 times 2, which equals 6. And x prime equals 1.25 times 2 minus 0.6 times 6, which gives us minus 2. Aha! So point S at 2, 6 transforms directly into S prime at minus 2, 6. Look at the red dotted line on our graph. It lands right there. What if we want to convert from the rocket frame back into Earth frame coordinates? Look at these inverse Lorentz transformation equations on screen. Again, if you have the version of the equation with both sides divided by c, please convert it to this form first. And notice how the minus sign simply flips into a plus sign. This is called the inverse Lorentz transformation. The concept is identical, but for a player inside the rocket, Earth looks like it's moving in the opposite direction, at negative v. So all you do is replace v with negative v in our Lorentz equations. In a single second, you're back in Earth frame coordinates. Let's check if it brings us back home with the same example. Transforming S prime at minus 2, 6. Ct equals 1.25 times 6 plus 0.6 times minus 2, which equals 6. And x equals 1.25 times minus 2 plus 0.6 times 6, which gives us 2. Boom! We're right back at S equals 2, 6. Isn't that totally seamless? Reading the map and using these equations give us the exact same truth. Wait, companions! Before we tackle the next big boss, here is a special pro tip bonus for our Lorentz transformations. Lies directly on one of the axes, you're super lucky. You can find the coordinates in a flash just by multiplying by gamma. Look at the top box on screen for points on Earth's axis. If position x equals 0, the second term, here, vanishes. Ct prime simplifies down to just gamma times ct. And if time t equals 0, x prime becomes simply gamma times x. Let's see this cheat code in action with our example on screen. If velocity v equals 0.6 c, where gamma is 1.25, and our point S is at 0, 4 on the vertical axis, Ct prime equals 1.25 times 4 minus 0.6 times 0, which gives us 5. Look at the graph. Point S at 0, 4 transforms straight to 5 on the Ct prime axis. Boom! Next, look at the bottom box for points on rocket's axis. It works the exact same way in reverse. If x prime equals 0, ct becomes gamma times ct prime. And if t prime equals 0, x becomes gamma times x prime. Check out the example. For a point S prime at 6, 0 on the slanted x prime axis, x equals 1.25 times 6 plus 0.6 times 0, which equals 7.2. See that on our map? S prime at 6, 0 drops right down to 7.2 on the Earth x-axis. Lock this ultimate cheat code into your brain. Coordinates on the axis? Just multiply by gamma. This single trick prevents calculation bugs and speeds up your quest solving massively. All right, team, time to challenge treasure number 2, the complete math hack for time dilation. We already saw this visually on our map, but now we're going to prove it with 100% mathematical precision. We'll keep using our rocket with a velocity of v equals 0.6 c, where gamma equals 1.25. Approach 1. Calculate specific values for E1 and E2. Look at approach 1 in the top right box here. Do you remember event 1 and event 2 from Earth frame S? Light was flashed at event 1 at CT equals 2, and event 2 at 4. Since both events lie on Earth's vertical axis, where x equals 0, we can use our axis shortcut trick. Just multiply by gamma. For event 1, CT 1 prime equals gamma times 2, which is 1.25 times 2, giving us 2.5. For event 2, CT 2 prime equals gamma times 4, which is 1.25 times 4, giving us 5. Subtract the 2. 5 minus 2.5 equals 2.5. On the graph, we could only guess roughly 2.5. But with math, we know with absolute certainty that delta C t prime is exactly 2.5. That feels super satisfying, right? Now, calculating 2 separate points every single time is a waste of precious quest time. Let's derive a universal formula in one hit. Look at approach 2 in the green box. Delta CT prime equals CT 2 prime minus CT 1 prime. Using our Lorentz transformation, this expands like this, and calculating this part, it's gamma C delta t minus v over c times delta x. Since both events happened at the exact same location on Earth, x1 equals x2, which means delta x equals 0. Substituting delta x equals 0 cancels out that second term completely. And look at what remains. Delta ct prime equals gamma times c delta t, which simplifies cleanly down to delta t prime equals gamma times delta t. Setting the single physical condition delta x equals 0 inside the Lorentz transformation instantly yields the time dilation formula. This proves mathematically that moving clocks run slower by a factor of gamma. Next up, let's go take down length contraction. All right, companions. Right after taking down time dilation, it's time to battle our next huge boss, length contraction, using pure mathematics. Let's do this. First, let's review a key physics fundamental. How do we measure the length of an object? We must measure both endpoints at the exact same time, simultaneously. In Earth frame S, measuring between Earth's world line and star's world line gives a distance of 4. On our graph, reading this from moving rocket frame S prime looks like roughly 3.2. Let's showcase its 3.2 with 100% mathematical precision. Look at approach 1 in the top right box. To measure length in rocket frame S prime, we need simultaneous measurement in S prime, which means time t prime equals 0. And from the diagram, we can see that we need to use our trusty inverse Lorentz transformation. This one. Setting t prime equal to 0 simplifies the formula to 4 equals 1.25 times x prime. Dividing 4 by 1.25 gives x prime equals 3.2. Boom! Delta x prime equals 3.2. Our visual guess on the graph is mathematically proven. Now, let's derive the universal formula in one hit. Look at approach 2 in the green box. We start with our inverse Lorentz transformation. X equals gamma times x prime plus v times t prime. In terms of distance intervals, this becomes delta x equals gamma times delta x prime plus v times delta t prime. Because we require simultaneous measurement in the observer's frame, delta t prime equals 0. That second term cancels out completely, leaving delta x equals gamma times delta x prime. Rearranging for moving length gives us delta x prime equals x over gamma. Look at the key takeaway at the bottom of the slide. Length contraction is a direct consequence of requiring simultaneous measurement in your frame. Outstanding work, team! We have now mastered both time dilation and length contraction. Next up, let's take on relativistic velocity addition. Are you ready for the next quest? All right, companions, after defeating time dilation and length contraction, we're finally face to face with today's final boss. Let's charge in and challenge relativistic velocity addition. By the way, some of you might be thinking, hey Elle, why don't we solve this on our spacetime graph? Here's the secret. Reading a moving target off a graph gets super tricky and can trigger serious brain bugs. That's why we use our Lorentz Transformation equations to solve this algebraically. Let's set up our scenario. Imagine a rocket flying at speed v relative to Earth. Inside the rocket, a pigeon flies forward at speed u prime as seen from the rocket frame. What we want to unlock is the pigeon's speed u as seen from the Earth frame. Velocity in Earth frame is defined as u equals delta x over delta t. Let's plug in our inverse Lorentz equations. Delta x equals gamma times delta x prime plus v times delta t prime. And delta t equals gamma times delta t prime plus v times delta x prime over c squared. Look at the screen. When we divide delta x by delta t, the gamma terms cancel out completely. Next, divide both the top and bottom by delta t prime. Since delta x prime over delta t prime is simply the pigeon's speed inside the rocket, u prime, we get u equals u prime plus v all over 1 plus u prime times v over c squared. You know, if you only look at the top part, u prime plus v, it looks just like the regular speed addition you learned in basic physics, right? That's the Galilean transformation. But in Einstein's universe, we get a special correction piece attached in the denominator, 1 plus uv over c squared. Now for Elle's hack. Let's test this formula with actual numbers to prove the ultimate cosmic speed limit. Suppose the rocket flies at v equals 0.6 c, and the pigeon flies inside at u prime equals 0.6 c. That's a pretty fast pigeon, but let's go with it. In old classical physics, you would just add 0.6 c plus 0.6 c to get 1.2 c, breaking the speed of light, right? But look what happens in Einstein's universe. Our numerator is 0.6 c plus 0.6 c, which equals 1.2 c. Our denominator is 1 plus 0.6 c times 0.6 c over c squared, which is 1 plus 0.36, or 1.36. 1.2 c divided by 1.36 equals roughly 0.882 c. Aha! It does not exceed the speed of light c. No matter how fast you add velocities, light speed remains the unbeatable maximum speed limit in our open-world universe. One last super important check for your exam quests. In your formula booklet, you may see the equation to calculate u prime from u, not u from u prime. Like u prime equals u minus v, all over 1 minus u times v over c squared. This is the formula to find the speed of an object moving at speed in the Earth's frame, as measured from the rocket. Don't panic thinking it's a completely new formula. Here's a really useful exam tip. As we saw before, from the rocket's perspective, Earth is simply moving in the opposite direction at minus v. So just replace with minus in our first equation, and boom, the plus signs instantly flip into minus signs. That one simple change gives you the entire equation. That is a 100% complete clear on today's main quest. Now, look at the slide to see where our space-time hacks connect to the real world. High-altitude cosmic ray collisions produce particles called muons, with a tiny lifetime of just 2.2 microseconds. Since they are produced high up in the atmosphere around 10 kilometers above us, even if a muon travels at the maximum speed limit, the speed of light, classical physics says they should never reach the ground. Yet, we detect them down here all the time. How is this possible? Suppose the muon zooms down at 0.98 c, where gamma is roughly 5. Look at the Earth reference frame. The phenomenon here is time dilation. For the muon itself, its lifetime is just 2.2 microseconds. But from our view on Earth, its clock runs 5 times slower, making its lifetime look like 11 microseconds. And in that 11 microseconds, the muon easily travels far enough to reach the ground surface. Now, let me flip to the muon reference frame. The phenomenon here is length contraction. From Earth's view, the distance from high atmosphere to the ground is about 10 kilometers. But from the muon's perspective, that distance contracts by a factor of 5 down to just 2 kilometers. The muon can easily cover that contracted 2-kilometer distance within its own 2.2 microsecond lifetime to reach the ground. Aha! Very important takeaway. Earth sees time dilation, while the muon sees length contraction. Different physics mechanics, but both frames calculate the exact same physical outcome. The muon reaches the ground. Isn't that a breathtaking resolution in this open-world game of nature? Nature's physical laws are completely consistent across all inertial frames. So, companions, how was today's grand quest? We trained on drawing space-time diagrams from scratch, mastered time dilation and length contraction formulas, and conquered relativistic velocity addition. Which part was your favorite boss battle today? Was it drawing the folded axes or deriving the formulas in one hit? Let me know in the comments below, or drop any brain bugs you hit along the way. You've gained a massive amount of XP today, team. Keep training, and I'll see you in the next quest. Let's keep leveling up!